Lift is the force that opposes the weight of the helicopter and allows it to rise into the air. Several factors influence how much lift is generated by the rotor blades. Let's define angle of attack. The angle of attack is the angle between the chord line of the rotor blades and the relative wind. Increasing the angle of attack increases lift up to a point. However, if the angle of attack is too high, the airflow over the blades can separate, leading to a stall or dramatic loss of lift. Let's talk about the rotor blade speeds. The speed at which the rotor blades move through the air is determined by the rotation of the rotor system. Higher rotational speeds increase the relative wind over the rotor blades, which increases lift. However, this also increases the drag, requiring more power. The shape and the design of the rotor blades, particularly the curvature or camber and thickness of the airfoil. A more cambered airfoil can generate more lift at a given angle of attack. The thickness of the airfoil also plays a role. Thicker airfoils can generate more lift, but also create more drag. The blade area is the total surface area of the rotor blade that interacts with the air. Larger blade areas produce more lift because they displace more air. This is why helicopters with larger rotor discs can lift heavier loads. Think of the Huey or K-Max or the Chinook. The air density is the density of the air which the helicopter is operating, which varies with altitude, temperature, and humidity. Lift is directly proportional to the air density. Higher air density, as found at lower altitudes and cooler temperatures, increases the lift. Conversely, where hot and high altitude conditions exist, where the air is less dense, lift decreases, which is why helicopters have reduced performance in such environments. Let's talk about the rotor blade design themselves. The design features of a rotor blade, such as twist, where the blade angle changes from the root to tip, and taper, where the blade narrows towards the tip. A twisted blade design helps distribute lift more evenly across the blade, reducing stress and improving efficiency. Tapered blades can reduce drag while still generating sufficient lift. Let's talk about some factors affecting drag. Drag is the aerodynamic force that opposes the helicopter's motion through the air. It is in the form of resistance that must be overcome by the engine's power. Drag is divided into three main types: profile drag, induced drag, and parasite drag. Each type is influenced by different factors. Profile drag is defined as drag caused by the frictional resistance of the rotor blades moving through the air. Larger blades create more profile drag. Airfoils with thicker profiles generally create more profile drag, but they also may generate more lift. Any roughness on the blade surface, like dirt or ice, increases the profile drag. Induced drag is defined as drag that results from the production of lift. It is caused by the vortices created at the tips of the rotor blades as they generate lift. The more lift that is generated, the more induced drag there will be. Higher angle of attacks increase the lift, but also increase the induced drag. Heavily loaded rotors, i.e. those generating a lot of lift relative to their size, produce a lot more induced drag. Parasite drag is defined as drag caused by non-lifting components of the helicopter, such as the fuselage, the landing gear, or any external equipment, police camera balls, or external spotlights. Parasite drag increases with the square of the helicopter's speed. This means as you fly faster, parasite drag becomes the dominant form of drag. A more streamlined helicopter shape reduces parasite drag. Anything that sticks out into the airflow, like antennas or skids, increases the parasite drag. Let's talk about the relationships between lift and drag. The lift to drag ratio is key performance indicator for any airfoil. The goal is to maximize lift while minimizing drag to achieve efficient flight. In helicopters, this balance is crucial for maintaining controlled flight and optimizing fuel efficiency. At lower airspeeds, induced drag dominates, while at higher speeds, parasite drag takes over. The helicopter is most efficient at flying speeds, often around 60 to 70 knots for many models. It is where the combined drag is minimized, allowing for the best lift-to-drag ratio, otherwise known as LD max. Lift and drag are influenced by multiple factors, including the angle of attack, airspeed, airfoil design, and air density. Understanding these factors helps pilots manage the helicopter's performance, particularly in varying flight conditions. All right, folks, if you've made it this far without dozing off, very impressive. Tip of the cap. Now that you're officially a helicopter nerd like me, why not take the next step? Check out my online helicopter ground school at 3gheliprep.com. Trust me, it'll only get more exciting from here, or at least more useful.